Essentially, we're going to first talk about what is Rust and why are we using it. So that's a big question that comes up a lot when people discuss a new language. There are a lot of people that, kind of need to be sold first on its usefulness. So we'll go over that a little bit. Then we're going to do a demo of my kernel module, and then we'll talk about leveraging existing kernel tools for actually building Rust. And last, we'll talk about the most interesting part, which is some Rust-specific gotchas. So things that you might not expect to bump into at a lower level and sort of how we can get around that. So first off, what is Rust and why are we using it? The reason for Rust tends to be that it's a highly systems-oriented programming language. It's very high performance. Despite it being a relatively new language, started around 2010, then it's actually made a lot of headway in that time. And so we get some really nice benefits like no garbage collection or manual memory management, and the allocations and deallocations really are handled by the compiler for you. It has a robust type system that is going to allow you to use unsafe to kind of opt out of those stricter security checks. And it's LLVM based, so it's going to give you a lot of those really nice optimizations. All of that together with kind of the existing ecosystem of out-of-the-box documentation and built-in testing capabilities kind of make it a really attractive option for a lot of people. So we'll talk a little bit about the safety guarantees. So Rust is strongly typed, so it's able to do some pretty intense type validation for you. It has ownership validation, which at a high level is what scope owns this data at what time. It's also able to do mutability validation, which essentially says when we have references, which of these references can mutate at a given time. And together, these provide some pretty attractive guarantees. So we're going to have memory safety, so no dangling pointers in safe Rust. We have data race safety, so we can't access data from two locations at any one time, and for write access. And these guarantees can all be overridden with the unsafe keyword. So who here is familiar with what an ABI is? Raise of hands. And who here needs a review? We can go through this. Okay, thank you. So an ABI at a high level is going to essentially be a standard of generated assembly that basically guarantees that when you link two things together that it will be compatible. So this includes things like consistent assembly instructions, data type sizes and alignment, and it's also going to be calling conventions and register usage. So this is very important when it comes down to interoperability between languages. So a lot of times we'll have interoperability between new languages and C kind of plagued by a lot of things like, driving the runtime and garbage collector from C. We'll have data type conversions that get pretty painful. We'll have to just explicitly write some bindings in C and kind of link that into our new language, or sometimes we even have to write assembly, and a lot of people like to avoid that. So Rust's approach is that you can explicitly coerce functions to really stick to the C ABI at compile time. And so we get some major benefits from this. One of the things that we're going to get is that we can link directly with C. And this is pretty simple compared to some of the other approaches I outlined. Rust actually is going to natively support in its build system linking C directly into the Rust program. So even the build system works with it pretty simply. And we really don't need any assembly for this whole process. So this overall is going to make Rust a very good candidate for kernel development. Anything that we are not able to offload to Rust, we're able to still do in C. So things like the C preprocessor are really going to need to be done in C. There's no kind of type-safe way to represent that. And particularly if we're accessing data fields in a struct that is kind of littered with if-defs, then at that point, we are really going to want to offload that to C as well. So we'll talk a little bit about the type system too. Rust is strongly typed, so we're going to get validation of data types passed into functions and validation of pass by reference versus pass by value. But both of those things can already be done by C. So what else does it kind of give us that we don't get in C? And some of these things are going to be things like explicit conversions only. So we're never going to have sort of a wiggly kind of typecasting system. We actually have to explicitly say how we're going to convert from one type to another. And so this really avoids some undefined behavior that could pop up. We're going to have type parameters, or generics as they're known in a lot of other languages. This is also validated and supported by the compiler. We have mutability checks. And what this is going to do for us is we have two rules. So we can either have one mutable reference and no immutable references to prevent sort of read-write corruption, or we can have as many immutable references as we want and no mutable references. So you can kind of think of it like a read-write lock at the compiler level. Ownership, we use move semantics, and so basically mutable and immutable references can be passed into functions, but essentially that does not constitute a move. Own data types will be moved when they're passed into a function, and they cannot be used in the original scope after they have been moved. These guarantee memory safety and data race safety, kind of as we talked about before. So when it comes to performance, we often get into a lot of kind of nitty-gritty number-related details, and people always want to know which is faster, C or Rust. And I'm going to kind of sidestep all of that because we're instead going to go over some non-controversial points. So Rust is going to produce native binaries. There is no garbage collection or VMs, so essentially we're going to get some performance boost from that. Rust uses LLVM as a backend, so anything that Clang has in terms of optimizations, those are also available to Rust. Rust is also going to use an intermediate representation, and what this allows us to do is Rust-specific optimizations, so that happens before we compile it down to LLVM. So when we're actually writing sort of more performance-critical code that really relies on some kind of unsafe pointer magic, then Rust also provides unsafe capabilities to drop down to that level and really do what we need to do. We can kind of think of Rust as generally in the same performance class as C and C++. And Rust's unsafe keyword, which we mentioned in the last slide, is going to allow us to do a few things. We can dereference raw pointers, we can call code that has been marked as unsafe, and we can access or modify mutable static variables. So these kinds of operations are often needed when we're doing some sort of FFI, and so this unsafe keyword is really kind of crucial for building C into the actual nuts and bolts of the language. So now we're going to have a little demo of my kernel module. So the kernel module itself is pretty silly, but it does do some really important things. So it's going to do some char device creation using the kernel API for that. It has some mutex locking in there. It's going to even be able to print out to the kernel logs, and it even does some buffer operations that are actually marked as safe and sort of encode the length in the buffers. So we don't really have to worry about buffer overflows here. So it's really just going to create an animation that when you cat the device node, then what it's going to do is it's going to display an animation. So first, I'll give you kind of the steps if you're looking to reproduce this on your own machine. And now we'll go through it. So here is my project directory.
Make it larger.
Here we go. Is that good? Yep. OK. So we're just going to run make. It's going to build this kernel module. We're going to insert the module. And now we're going to check the logs for the major and minor number. And /dev/parrot. Here we go. So what does this kernel module do? We party hard. So how did I do this? Well, I leveraged actually a lot of existing tooling for the kernel. So we have here a list of basically all of the tools you'll need for this. But the most important one really is kbuild, because that is the native system for the kernel builds. And so we're actually able to leverage that because of Rust's C-ABI compatibility to actually offload a lot of this. So what changes? Well, we're going to have to do something a little bit more manual to basically create our object files. And we'll have to do a few function declaration level changes on the Rust side. And the way the kernel API methods are handled on the Rust side will also have to change. So kbuild really is going to be the easiest way to accomplish this task, because it's makefile based and accepts C-ABI compatible object files. And it's also, going to be semi-shell based. So we're able to call into different tools that we need in the Rust ecosystem. We will need to download some devel packages. And while the kbuild documentation is pretty dense, usually it will give you everything you could possibly need to know for something like this. One note that you should definitely put a bookmark in is that it's going to ignore static libraries. So this actually comes into play later. As for Rust side changes, we'll have to make two specific changes that are really important here. One is going to be an attribute that we attach to the functions for entry points, that is no mangle. And one is going to be just declaring this as compatible with the C-ABI as an extern function. Overall, the rule is that we should keep everything compatible with the C-ABI. So for example, we're going to want to use pointers instead of references, and similar kind of C-ABI compatible data types that map directly to Rust data types, but have a little bit less information encoded. So no mangle is really important, because by default, C is going to assign a label that essentially just kind of maps from this entry point in the kernel to this label right here. So it's really a one-to-one correlation. Rust is actually going to mangle the symbols. So we have a init module, and it's going to take it out of the global namespace by mangling it, as we see right here. The solution is that on kernel entry points, we just attach no mangle to the top of this function, and we're going to get the unmangled symbol. When we actually talk about extern C function declarations, then one note is that this is not going to validate that everything you have done is CABI compliant. So there is some work that you have to do to make sure you're doing everything correctly. However, this is because not everything that is in Rust is actually compatible with the CABI. You can force it to become that way, but it's not going to be that way by default, and this should be relatively intuitive because ultimately we're representing things that are just not representable in the C-type system. So data types really must conform to the CABI, so we'll have integer primitives that are acceptable, anything in the libc crate, and pointers to any of those acceptable types. We can also mark structs as specifically CABI compatible, and this is going to exclude a lot of things like vectors and slices and a lot of other data types that we just can't use. So slices will not work because they encode length and pointers do not. References also encode additional information that pointers do not. We're not going to be able to use U128s because C does not support those at the CABI level. And we're also going to have to mark those structs as explicitly CABI compatible because of memory optimizations that Rust will do for us. So we should talk a little bit about libcore because this is going to be everything that we need in terms of basically a standard library. So you can think of libcore as the standard library for embedded or systems work that's basically going to allow you to define your own allocation and do a little bit lower level things like that, that essentially the standard library itself is going to take for granted. So we're going to need to include this somehow in our build. So it actually gets a little bit more complicated than I was originally thinking. Rust can output a number of different output options, but ultimately we're going to want to go with static libraries. So as you might remember, static libraries are not compatible with kbuild, so we'll have to take some manual steps to actually make sure that this is going to properly work with kbuild. So this is a little bit more manual than some people might like, but it does work consistently. And because static libraries really are just archived object files, what we're going to want to do is basically unarchive that static library. And then with LD, we can just link all of those object files together. And we're going to get an object file that actually gives us exactly what we need. This object file basically can then just be passed directly off to kbuild. So now we're going to talk about some Rust-specific gotchas. So this is really defined in kind of 3 different levels. So we're going to have the symbol level, we'll have the foreign function interface level, and then we'll have global state immutability. So at the symbol level, we've already kind of touched on no mangle, so I'm not going to go over that again, but we also need some build-specific changes. For example, if you're doing this all manually, then you will have to make sure that your code is compiled with some flags, for example, to put it in kernel address space and basically use the procedural lookup table instead of the global offset table because of the nature of the kernel address space. Now, all of this can kind of be avoided and really has to be avoided because of libcore. So when you're building normally with Cargo, the native build system, then what it's going to do is it's going to link in a pre-compiled libcore for you. And when you do that, then essentially you don't have any control over what options that's actually been compiled with. When you start linking it in, your code that you wrote might have the appropriate flags for the compilation. However, libcore is not going to have that. So really the only way that I found around this is to use Xargo, which is a cross-compiler for both your code and libcore. And then thankfully, they were nice enough to put a Linux kernel target in that for us. So this is going to be a lot simpler. Now at the FFI level, we have a few options. So we have BindGen, which is a tool that can generate bindings from C headers, actually. But this is not really going to work for us because BindGen doesn't actually work with the kernel headers. Now we can do DIY bindings, and some of that is really necessary because this is the only way to expose kernel methods directly from kernel space into our Rust code. This gets a little bit messier because we actually have to make sure that our data types match up directly between the kernel API and our API that we've exposed. So this one should be done with caution, but it really is the only way to expose kernel methods directly. We can also wrap kernel API calls in kind of safer C functions that have fewer parameters. And this is actually really necessary when we're doing things with the C preprocessor macros, because when we get into that area, there's no way to translate that across the FFI boundary. So really, this is going to be a large part of what you end up having to do a lot of the time. Now, definitely examine the trade-offs carefully because all of these options have different places and different kinds of FFI. And the rule of thumb that I would say is if you're doing something with the C preprocessor macros, then essentially, or anything with structs even that have if-defs in them, you'll want to offload that to C because you may want to try to win that war, but you will not. So this was kind of the most fun part. Really what we're going to do here is kind of say, how can we get idiomatic Rust outside of everything that we've built on top of? So one option that I chose for actually providing a safe interface to global state mutation is that I actually designed a mutex that kind of has a similar pattern to the standard library that actually wraps the kernel mutex functionality. So it's going to really give us that ability to kind of keep the Rust promises that the language requires while also giving us a little bit more idiomatic Rust code. So here we're going to take a look through some of this code. We essentially have our inner data type, and so that's going to house our data that we're protecting. We can actually immutably acquire a mutex lock. So when we do that, we're calling into C, which is going to call the kernel API, and then we get this mutex guard returned. This mutex guard basically has a lifetime. That means as long as it is in scope, it will keep that lock acquired. We can get a mutable reference from that mutex guard, and then once it goes out of scope, that's what drop is for, then essentially it will unlock the mutex. And so here what we're really getting is that the mutex guard is basically going to clean up after us. And so we really don't have to worry about data races here. We're essentially guaranteed that Rust is going to clean up after us. And this is one of the major benefits of the language. It's going to protect us against programmer error. So in summary, we can kind of take a few things away from this. There definitely are going to be some additional challenges using Rust, and some C is definitely still required. But Rust's benefits really can be used effectively in the kernel. We can kind of get a lot of things for free in terms of resource management and cleanup without really a performance hit. And ultimately, there was a whole lot less unsafe than I thought was initially going to be required. So thank you for attending. Here is the link for my source code if you want to take a look through that and see more, if you want to see just sort of a more in-depth example of this. Thank you very much.
Any questions? So I've seen a couple other Rust and Linux kernel projects, and I'm just curious how many others you have looked at and what you explored before you did this.
So I actually I've looked at maybe one. When I started this project a while ago, I looked around a little bit for this, and I was actually unable to find very many when I started this. I'm not usually sure what the approach they take is, and the purpose of this one was basically, instead of really getting down into the weeds of exactly how we can do everything from scratch, this really was intended to be, how can we make this as easy as possible? And that's ultimately why I did this project.
In the beginning, you showed TOML file and some console output, and I saw that you use Rust nightly. Does it mean that you cannot build your code with stable Rust?
So Xargo is going to require nightly. Because of the Linux kernel target, you will require nightly for now. I'm not sure what the plans are for stabilizing that, but right now it does require nightly.
Okay.
Any more questions? Well, we'll wrap it up early there then. Thank you all very much.